So now that we have the balancing of redox reactions all figured out, what we can do now is start applying them to actual practical conditions where we can enact a chemical change through the transfer of electrons. And the best example probably of this is if you put reactants together and they start reacting. It's like a battery that works, all right? And those are important. And again, they call batteries that work essentially galvanic or voltaic. Their product favored electrons start flowing. So as an example of this, in the upper right-hand corner, you can place a piece of zinc metal, which comes as a strip, in a copper 2+ solution. And copper 2+ has kind of that cool blue color. And what happens is right away, the chemicals start reacting. Zinc gives up its electrons easily. It's oxidized. Copper 2+ loves to take those electrons to make copper metal. Copper 2+ likes to be reduced. This is what they call a direct redox reaction. They're very high yields, all right? You have a very high turnover. Zinc goes to zinc 2+ and copper 2+ goes to copper metal, which is really neat. However, you don't have any control over the reaction. So you start putting the reactants together and you're like, oh crap, I didn't want to put those together. Well, you could take the piece of zinc out, but there's no other way to stop the reaction. So direct redox reactions do have their use, but we're going to talk about the indirect redox reactions, i.e. batteries, more in just a sec. This reaction on the right shows a similar reaction, but now it's copper metal reacting with silver plus ions, and copper 2+ is made and silver metal is created. And this is also a reaction which is going to happen. It's going to be spontaneous. Its delta G Gibbs free energy value will be negative, and people call this galvanic cell or voltaic cells, same thing. So in this kind of reaction, you also have something spontaneous, but the difference here is that now we have a control over how reactions will actually happen. Like if we wish to stop it, we can, or we can just let it go, either way. So in this reaction, notice that copper is going to copper 2+. So copper is giving up electrons. And as copper gives up electrons, the electrons now are going to flow in a wire. So in red here, I have the directions that the electrons will travel. And notice that there's a negative and there's a positive. Well, electrons are negative. They want to get away from the negative side and they want to go towards the positive side. So electrons are going to go from the copper to the silver piece of metal, which is in solution. And they're going to go right down the metal because metals transfer electrons, no problem. And it's going to turn the silver plus, which is in the solution, it's going to turn the silver plus into more silver metal, which is pretty cool. That's what happens when the electrons go through the silver to the silver plus. It makes more silver metal. So you can imagine then that the silver metal is kind of filling up here on the bottom. Well, the problem here is that as silver plus goes away, you can't just add silver plus. It has to come with something different. And it most likely is going to be a nitrate ion. Well, as nitrates build up, you get more and more negative nitrates running around. So that kind of stops chemical reactions from happening. So what scientists do is they put between the two sides, they put what's called a salt bridge. Salt bridge is usually like an agar or essentially like a type of seaweed kind of holding U-tube thing. And what happens is negative ions will flow from, in this case, the silver side to the copper side. So the negative ions are flowing from the right to the left, if you will. And that's a good thing because as the copper gives up electrons, you have more and more copper 2+. So you need more negative ions, i.e. nitrate, this time from the silver side, in order to balance that out. So here's what's cool about this. Electrons are going from the copper to the silver through that kind of top part right there. And then nitrates, which are negative, are flowing from the left to the right. And then you have more electrons going there. This, my friends, is like a type of electron highway. Electrons will travel from the copper to the silver, and then negative nitrates, which are a source of negative electrons, will flow through the salt bridge from the silver side to the copper side. So you've got electrons constantly moving around and around and around. And this is now called an indirect circuit. You're able to control the chemical reaction. You can turn it on and off as you want. You could put little light bulbs on the top to see the electrons are flowing. You could have an on-off switch, which is cool. It's really fantastic. So in this kind of cell, which is what they call a galvanic or voltaic cell, which just means electrons start flowing, electrons will flow from the oxidizing site, this part that's losing electrons. So that's why that site gets a negative charge. It's called the anode. And electrons will flow from the negative anode to the other side, which in this case is positive. They call that the cathode. So electrons you see are flowing from the anode to the cathode, which is pretty cool. So that's what happens in a galvanic cell. And again, the advantages of this is that chemists can control it. When you put the zinc metal directly in the copper 2+, the reaction just went crazy. And you could do the same thing here. You could put copper metal in silver plus, and silver would start forming, and blue copper 2+ would form, but you wouldn't have any control over it. This way, with the salt bridge and the wires and stuff, you can actually control the electron flow, which allows you to control how current is distributed, and that's the idea behind a battery. So in this question, we want to find the reducing agent in the reaction. And reducing agent and oxidizing agent, for that matter, always refer to reactants. So the answer here will be nickel or silver plus. It will certainly not be the nickel 2+ and the silver, because those are products. Also, we know it is a redox reaction because nickel is changing charge as it goes from reactant to product. Nickel's going to a positive 2. Silver plus is becoming less positive as it goes to silver. So reducing agent, you have to remember, reducing agent means that it's being oxidized. All right, so we're looking here for the species that's being oxidized. Oxidized, lose electrons. Oxidized, that means something's becoming more positive. And if you look at this long enough, nickel is going to nickel 2+. It's becoming more positive. It's losing electrons. Nickel is being oxidized. And something that's oxidized, you guessed it, is the reducing agent. So reducing agent means oxidized. Silver plus is being reduced to silver. That means silver plus is the oxidizing agent in this reaction. Keep those in mind. They can get confusing, but it's nothing you can't handle. There are different expressions that might help you in these next areas, and they're kind of silly, and some people like them and some people hate them, so don't feel like you have to use them. But anyway, if they do help you, I think it's worth talking about. First one is a red cat. Reduction occurs at the cathode. So if you have, for example, copper 2+ going to copper, that would be the cathode, because copper 2+ is gaining electrons to become copper metal. On the other hand, an ox would be oxidation at the anode. So zinc going to zinc 2+, zinc is being oxidized. That would mean that zinc would be at the anode. So reduction at the cathode, and zinc would be oxidizing at the anode. And more importantly than anything, just note that reduced and cathode, they both begin with consonants, while oxidized and anode both begin with vowels. Now, if you haven't thought about vowels and consonants for a while, I understand. The vowels are A, E, I, O, U in the English language. And notice that ox and an both begin with vowels. So they go together. On the other hand, the consonants, which are everything but the vowels, are both R and C in reduction and cathode. That's how I usually think about them. But some people like the red cat and the an ox, which is fine too. And finally, oxidation means reducing agent and reduction means oxidizing agent. So just remember that. If you see the agent, it's like the opposite of what it's trying to imply. I hate it, but again, I'm just the messenger here. So something that's being oxidized is the reducing agent. Something that's being reduced is the oxidizing agent. The salt bridge is just some kind of material that allows the ions to flow through. The most important ions for us is it's going to flow from the cathode to the anode. You do have a little bit of counter ion moving the other way, but we're not going to worry too much about that. But the idea is that as the silver plus becomes silver, you no longer have as much positive charge at the cathode. So those negative anions are going to go over to the other side, the anode. They will take the place then and help out the copper copper 2 plus ions which are forming. Copper 2 plus needs an anion to make it balanced. It just is all about keeping everything neutral. And if you do this, the important part is that electrons literally flow from the anode to the cathode, and then anions flow from the cathode to the anode through the salt bridge, which is pretty cool. We used to make salt bridges when I was in graduate school, and again, we used a type of a seaweed and agar kind of stuff, and you have to let it soak for a while, and it kind of stunk, as I remember. But again, they're not too hard to create, and they do keep the electrons flowing, which is what you want in these kind of systems. Instead of drawing out an extensive anode-cathode combination, a lot of times people will use shorthand notation. And this is specifically the shorthand notation for galvanic cells. Galvanic or voltaic cells are the ones that start working when you put them together. They're spontaneous product favored. So the copper 2 plus and zinc reaction going to zinc 2 plus and copper metal can also be written in this little piece down there. And at first this is a little weird, but it's not too bad once you know the rules. First of all, the main rule is that electrons always flow from left to right. So just like people read in the English language from left to right, electrons flow left to right. So what that means is zinc going to zinc 2 plus, that's going to be the oxidizing part. Zinc is being oxidized. And then copper 2 plus and copper, that means copper 2 plus is going to gain electrons to become copper metal. So electrons come from the zinc side and they go to the copper side. That's kind of what that implies. Now, as something is being oxidized, it's also known as the anode. Remember, ox and anode, anox, or they're both vowels, whatever you want. The anode's on the left, and something that's being reduced is at the cathode. So reduced cathode, red cat, right? They go together, whatever consonants, whatever you want. So anode on the left, cathode on the right. Now there's single lines and double lines. Single lines just imply a phase boundary. So for the zinc, that would mean going from a solid zinc to an ion, an aqueous ion. So that's the phase boundary. You're changing what it looks like. Copper 2 plus going to copper is the same. You're going from a solution to a solid on that phase boundary, but same idea. The double line in the middle implies a salt bridge. That's where the ions are going to have to flow from one side to the other to keep everything electrically neutral. So if you understand how all of this works, it is a lot more convenient. You can write this in, say, Microsoft Word. You don't have to draw out the elaborate oxidize, reduce, salt bridge, all that kind of stuff. This is the shorthand version, which can be really helpful when talking to colleagues. Fat cat is another expression that's sometimes used in this area. Electrons flow from anode to cathode. From anode to is fat, cathode. Anyway, I don't know if you like any of these things. I think I just like showing pictures of cats. You know, it kind of cracks me up. Anyway, weird sense of humor in your instructor. But anyway, fat cat can help you learn this stuff too. So let's describe this reaction using our knowledge of what shorthand notation is all about. And you can see there's copper and copper 2 plus on the far left. And then starting in the middle and going to the right, you've got chlorine, Cl2, going to chloride. And there's also platinum solid on the far right. So let's make sense of all of this. Well, first of all, electrons are flowing from the left to the right. All right. So that means copper is going to copper 2 plus, and in the process, 2 electrons are created. The copper 2 plus concentration, the moles per liter, is 1.0 moles per liter. So the 1.0 moles per liter tells you the concentration. That'll be important to us. We'll talk about that in a little bit. Then you've got the salt bridge on the other side that separates the two compartments. And on the other side of this, you've got chlorine going to chloride. Remember, electrons are always flowing left to right. So chlorine, Cl2, is gaining 2 electrons to become 2 chlorides, all right? And along the way, the chlorine gas, which is a gas, by the way, it's one of the red elements if you have a periodic table that shows the phases. Chlorine is a gas at 1.0 atmospheres. That's the pressure of the gas. And the chloride on the other side too is at 1.0 moles per liter. So those are the concentrations and the pressures of the gas. It's the gas that's accepting the electrons to make chloride in this case. Now, on the chlorine side, chlorine's a gas, chloride is a solution. You don't have any way to transfer the electrons from the copper side into the chlorine unless you put a platinum electrode in. And it's very common to use platinum, sometimes nickel, palladium, stuff like that. They're usually pretty inert metals that will transfer your electrons in. So the platinum is allowing the electrons to go from the chlorine gas to the chloride. That's why it's included right there. Most of the examples we've seen have had a metal as either reactant or product, but in this case, chlorine going to chloride, you don't have a metal. You need a platinum electrode to transfer those electrons in. In this question, we want to know what species is being oxidized, and it shows a shorthand notation. All right, well, oxidized means losing electrons, so we want to figure out what species is losing electrons. And remember, electrons move from left to right in the shorthand notation. So that means zinc is going to zinc 2 plus. Zinc metal, zinc solid, is going to lose 2 electrons to become zinc 2 plus. Zinc metal is the part being oxidized. All right, electrons are going left to right. The gold plus, which is Au plus, by the way, the gold plus is going to accept the electron or electrons to make gold metal. So gold plus is gaining electrons, it's being reduced, but the zinc metal is losing electrons to become zinc 2 plus.